Hello once again. It's the Rusty's Brosis Learning Together session once again. And this time we're going to be continuing what we started last session. We discovered that rational expressions are actually very involved. Not difficult, but very involved. So we worked on rational expressions last time. And I did promise that if it takes 3 sessions, it's okay. So today we're going to continue where we left off. And if time allows, we might be able to start working on rational equations. If not, we will pick up on rational equations next time. So what are rational expressions? Rational expressions are just fractions that have variables in either the numerator or the denominator. So the only difference between a regular fraction and a rational expression is that with a rational expression, you introduce a variable into your fraction. Okay, good. So last time we were working on different examples, and I'm going to look at an example that we could work on even right now. For example, let's do one that has division. Okay, say if we had x squared minus 49 over 2y cubed divided by x plus 7 over 8y to the power of 5. We might have done an example like this last time, but that's okay. Nothing wrong with refreshing. Okay, so we discussed that whenever you divide by a fraction, we flip the divisor and change the division to multiplication. We also realized that if it is possible to factorize anything, we will get a lot of benefits if we do that upfront. So this is a difference of squares. It's actually x squared minus 7 squared. Okay? So that we know can be factorized as x plus 7 times x minus 7. That's what this is equivalent to. So it's that over 2y cubed times. And now we're going to change the division to multiplication, and we're going to flip the divisor. So this now becomes 8y to the 5th over x plus 7. Now, this x plus 7 cancels this x plus 7. This 2y cubed goes into this 4y squared. And so therefore, our final answer is going to be 4y squared times x minus 7. So from here, we end up here. And that is going to be our final answer for that question. Okay? Another one. I promise you we're going to do some more complicated examples today. So here is another one. So this is number 2, x squared plus 3x over x plus 2 plus 2x plus 6 over x plus 2. I think I did this one too. But let's see, we already have a common denominator, it's already here, and it's a plus. So we can put the 2 expressions together. So that's going to be equal to, it's already same denominator. So now we can put the numerators together. It's going to be x squared, 3x plus 2x is 5x plus 6. And this, we realize that the top can be factorized. If you notice, I'm trying to put the vinculum right smack in the middle of the equal sign. This is called the vinculum. And that's vinculum. Just a little trivia, vinculum. Okay, so the bottom is x plus 2, and the top is going to be x plus 3 times x plus 2. Remember, this session is not about learning to factorize. That is already taken care of in an earlier session. So when you reach this stage where you're working with rational expressions, you must know how to factorize. So then when we look at this, we realize, okay, this is the same as that. They cancel. So our final answer is x plus 3. Okay? This was just to warm us up so we get into more complicated. So let's go to number 3. Again, we're working with rational expressions. We're trying to go through the skills that you will need so that you can be comfortable. When we see this one, okay, let's try this one, number 3. Let's try 6y plus 13 over y squared minus 4y minus 21 minus, watch that now, that's a minus sign, y minus 2 over y squared minus 4y minus 21. So my recommendation is factorize, because when you factorize, you will have a chance to cancel. If you don't factorize, it's going to be very hard to reduce or to simplify. So same denominator, so we can put them together. And of course, let's factorize this. It's going to be y minus 7 times y plus 3. Okay, that's the factorization of the denominator. Okay, this of course is a square. Okay, what happens to the top? Well, it's going to be 6y plus 13 minus y minus 2. Notice you're subtracting everything that's here. So it is recommended that you put in your parentheses, so you are very careful to subtract everything that's to the right of your minus sign. Okay, if you don't put the parentheses, you might end up putting minus y minus 2, and that will be incorrect. Okay, so now we go, draw our vinculum, y minus 7 times y plus 3. And then this becomes 6y minus y gives me 5y. And then 13 minus minus 2 is 13 plus 15. 13 plus 2 gives us 15. Let me quickly check that. If you're minus and negative, you will get a positive. 13 plus 2, 15. If you see this, you notice that 5y and 15 can be factorized. So we end up with 5 times y plus 3 over y minus 7 times y plus 3. Now you can see why we factorize, because now you have a multiplication by multiplying by y plus 3, multiplying by y plus 3. So this cancels that. So your final answer is going to be 5 over y minus 7. I think you're getting the drift. Now, the next one is going to take it like a curved ball. This one is going to be like a bouncer for those who play cricket. Watch this one. Most of my students get a little nervous when they see this kind of question, but we're not scared. We're not scared. So this is going to be number 4 is 1 over y squared minus 1 all over 1 plus 1 over y. Yes, I told you, I warned you. This is ugly, really ugly. So we have a fraction minus a whole number, and a whole number plus a fraction. So you have an ugly expression as a numerator, ugly expression as a denominator. So what do we do? Well, my recommendation, combine these two and make one fraction, combine these two and make one fraction, and now you'll have a fraction divided by a fraction, so we know we flip and multiply. Okay, so here we go. This is the same as 1 over 1. This is the same as 1 over 1. So I want to make that clear so we can see that a whole number is a fraction. If I gave you the number 6, I can write that as 6 over 1. That's why 6 is called a rational number. Remember, rational numbers can be written as fractions. So a whole number is a rational number. Just put it as that number over 1, and it's perfectly equal. Okay? So here we go. What does the top become? Well, let's go. This is equal to, that's our vinculum, and now we're working with this. Our common denominator is 1 times y squared. So our common denominator is y squared. This was already 1, nothing changes. This, if I change this bottom to y squared, I have to change the top to y squared also. Look what happened. Multiply the bottom by y squared, I got y squared. So I have to multiply the top by y squared, there's y squared. Let's go this way. If we had, say, 2/5, and I want to change that to a denominator of 20. This is a sidebar. I have to multiply 5 times 4 to get 20. So therefore, I also have to multiply the top by 4, and that's 8. So I'm saying to you that this fraction is equivalent to that fraction. Why? Because all I did, I multiplied the top by 4 and multiplied the bottom by 4. So it's an equal fraction. I could now here reduce this by dividing the top by 4, I get 2. Dividing the bottom by 4, I get 5. 2/5. Okay? And that's perfectly allowed. That's equal. These are called equivalent fractions. If I multiply the bottom by 4 and I multiply the top by 3, then I get 6 over 20. That's not equivalent to 2/5. In order for it to be equivalent, I have to do the same thing to the top as to the bottom. I have to multiply the top by the same number and the bottom by the same number. Or in other cases, I have to divide the top number by the same thing as what I divide the bottom by. So as long as you're multiplying or dividing the top and the bottom by the same number, you're good. Let me quickly say, you cannot add the same number to the top and the same number to the bottom. It will be a different fraction. You cannot just subtract the same amount to the top and bottom. It's a different fraction. So it only applies for multiplication and division. Okay, just wanted to get that out there. Let's deal with the bottom. The denominator is y. Common denominator is y. So if I change the bottom here to y, I have to change the top here to y. Multiply this by y, multiply that by y. So I end up with y plus, this is already 1 over y, so this is 1. Okay? So now we have a fraction divided by a fraction. So we can put equal. So now I'm going to write this, multiply by this when flipped. So it is 1 minus y squared over y squared times y over y plus 1. Okay, so here we go. This is actually 1 squared minus y squared. So this is a difference of squares. So I can actually factorize this using the difference of squares concept. So this becomes 1 plus y times 1 minus y. That's what this is. And just to check, to make sure that we're correct, 1 times 1 is 1. 1 times negative y is negative y. Y times 1 is positive y. Negative y plus y is 0. And then y times negative y is negative y squared. So it is perfect. And now we have that over y squared times y over y plus 1 is the same as 1 plus y. That's called the commutative property. C-O-M-M-U-T-A-T-I. That's the commutative property. That is, A plus B is the same as B plus A. The order doesn't matter. Similarly, A times B is the same as B times A. The order doesn't matter. If I have 2 plus 3, it is 5. 3 plus 2 is still 5. If I go 2 times 5, it's 10. 5 times 2 is still 10. So the order you put the numbers do not matter. However, if you're subtracting, 5 take away 2 is 3, but 2 take away 5 is negative 3. So subtraction is not commutative. The order matters. Similarly, division. 10 divided by 2 is 5, but 2 divided by 10 is 1/5. Division is not commutative. Okay, that's a little extra stuff. So where do we stand now? So this, I could write this as 1 plus y. So if you look, you see that this cancels that. You see that y cancels the square, so just strip the y. So our final answer is 1 minus y over y. So this is where we came from. This is where we end up. Kind of ugly. So let's walk through the process. What did we do? We combined these two expressions and made a fraction. We combined these two expressions and made a fraction for the denominator. So now we have a fraction divided by a fraction. And what do? Well, hey, when you divide by a fraction, you flip and multiply. So we flipped this, becomes y over y plus 1, and then we change the division to multiplication. That's it. Let's see if there's another example like that, because this is good practice for us. Yes, there's another example coming up. Yes. Okay, I think we're making good progress. Let's try this one. Number 5. 5 says 25 over a minus a, and that you want to divide by 5 plus a. I'm just copying it exactly the way it is given. 25 over a minus a, all divided by 5 plus a. Ready? In the previous question, we had a fraction on top and a fraction on the bottom. Now we just have a fraction on top. So this looks like it's a little easier. So do we agree that we could put a as a over 1? Dividing by 1 doesn't change the value. It's the same thing. But we do it so we can see our common denominator. So here we go. The vinculum is here. The bottom remains as 5 plus a. Nothing fancy at the bottom. But this becomes the common denominator of a. A times 1 is a. You already have 25 minus. This denominator changes to a. A times 1 is a. So we have to multiply the top by a. We end up with a squared. then we come here. So now we have, this is 5 plus a over 1. Anything you have, any expression, you can write it over 1 because dividing by 1 does not change your value. But when you put it like this, it becomes easier to see the next step. When you put it like this, over 1, you can see that, okay, this is a fraction, you're going to flip and multiply. And that's the easiest way to transition from here to the next step. So now we have 25 minus a squared. Do you recognize that this is also a difference of squares? This is 5 squared minus a squared. And we know the factorization of difference of squares. We end up with 5 plus a times 5 minus a over a. I always like to write the vinculum in line with equal sign. It's just aesthetically better. Times 1 over, when you flip this, it's 1 over 5 plus a. And now you can see clearly what the final answer is. This cancels that. And now we have 5 minus a all over a. That's your final answer. So this becomes 5 minus a over a. Okay, we're getting somewhere. Let's move it. Number 6. Number 6 goes like this. 4 plus 12 over 2x minus 3 all over 5 plus 15 over 2x minus 3. That's what they give me, that's what I give you. Okay? So this is a vinculum. So we have a whole number plus a fraction, a whole number plus a fraction. So we could start by changing this 4 to 4 over 1. Changing this 5 to 5 over 1. And now we're going to get the common denominator is 2x minus 3. So this is going to become 2x minus 3. So let's see. What did I do to the bottom here? I multiplied by 2x minus 3. So therefore I have to multiply the top by 2x minus 3. So now we end up with 4 times 2x minus 3. That's what you have to do to the top, so that the bottom and the top become the same. Okay? This was already 2x minus 3, so I just need to put plus 12. What about the bottom? The bottom here is going to become 2x minus 3. So this becomes 2x minus 3, so I have to multiply the top by 2x minus 3. So I end up with 5 times 2x minus 3. And then this is a plus 15. Okay, so here we go again. We have a fraction divided by a fraction. So what do? We flip and we multiply. Okay, so now we have, and if you will allow me, I'm going to expand at the same time I can see where I'm going. So now we end up with 4 times that gives me 8x minus 12 plus 12 over 2x minus 3 times. When I flip this, I end up with 2x minus 3 over 10x minus 15 plus 15. See that? 5 times 2x, 10x. 5 times negative 3, negative 15. Plus 15, plus 15. And what does that give us? Well, this cancels that. And this here becomes 8x over 10x. This cancels that, so it's over 10x. Do you see that the x's cancel? So therefore, the final answer is going to be 4/5. That's our final answer. Wow, from this ugly to this. It's not a beautiful thing? Cancels out, and this is what we end up with, 4/5. Okay. I think, wow. Here's another one over here. Let's see if we could, yeah, we have a couple more tricky ones. So I think it's good to do those. And then we will consider rational equations next session. Yes. So number 7. I still think I might be able to do a couple simple ones. So here we go. This one is more complicated. So this is, I think, number 7. We go 1 minus 12 over 3x plus 10 all over x minus 8 over 3x plus 10. Okay? So you agree that we can put this over 1 and this over 1. Okay? I'm going to make this into a fraction, and then business as usual. I think you're getting the drift. So this is going to become over 3x plus 10. And then the top here is going to become, this is going to become 3x plus 10. So the top has to be 3x plus 10. So 3x plus 10, and then we're minusing 12. And for the bottom, this is going to become 3x plus 10. So I have to multiply the top by 3x plus 10. So it's going to be x times 3x plus 10. And then it's going to be minus 8. So once again, we have a fraction divided by a fraction. So what I'm going to do now, I'm going to flip this, but while flipping it, I'm also going to expand the parentheses. So we now have, the top becomes 3x minus 2 over 3x plus 10. And now instead of division, we're now going to have minus as multiplication. This goes to the top, this goes to the bottom. So it's 3x plus 10 over, when I expand this, I end up with 3x squared plus 10x minus 8. So I'm going to need to factorize this. And I see that these two cancel each other. So now we end up with 3x minus 2, because this cancels that. And now when I factorize this, I think we're going to end up with 3x minus 2 times x plus 4. Let's double check to see if it works. 3x times x, 3x squared. 3x times 4, 12x. Negative 2 times x, negative 2x. 12x, take away 2x, 10x. Negative 2 times positive 4, negative 8. So we're good. And now we see that this cancels that, and we end up with x1 over x plus 4. So we went all the way from here, and this is what it simplified to give. Okay? Okay. This will be the last one of this kind. Yeah, the last one of this type. Oh, really? No. I see another. I see two more. Let's do two more. Okay, so this is number 8. It says, you see the reason why I did this one. It's 1 over a minus 3 over a minus 2 divided by 2 over a plus 5 over a minus 2. So this one, a lot of things going on right here. A lot of things going on. Let me make sure I copied it correctly. 1 over a minus 3 over a minus 2, all over 2 over a plus 5 over a minus 2. Yes. As before, we're going to make a fraction on top and a fraction on the bottom. So here's our equal sign. Here's our vinculum. And here is for our fraction. So the common denominator is the product of these two denominators. So we have a times a minus 2. And this, now we have to multiply this by a minus 2 to get that denominator. So we need to multiply the top by a minus 2. That's a minus 2. Minus this, we have to multiply by a to get this denominator. So therefore, I need to multiply the top by a. I end up with 3a. Let's go to the bottom. Same thing at the bottom. This and this gives me a times a minus 2. And the top, I have to multiply by a minus 2. So I end up with 2 times a minus 2 plus the bottom here, I have to multiply by a to get this denominator. So I have to multiply the top by a. So now we have a fraction divided by a fraction. So I'm going to flip and multiply. And in the process, I'm going to also simplify that numerator and that numerator. So here we go. This becomes a minus 3a minus 2. So a minus 3a is negative 2a minus 2 over a times a minus 2. So that's the top. Then I'm going to multiply. This goes to the top, this goes to the bottom. Multiply by a times a minus 2, all over, and now I'm going to expand this. 2a, 2 times a is 2a, and this is 2a plus 5a is 7a. 2a plus 5a is 7a. 2 times negative 2 is negative 4. Okay? When you look at this, you see that this cancels that. Okay? When we look at this, we notice that there's a negative 2 that's common. So I could write this as negative 2 times a plus 1. Let's check. Negative 2 times a, negative 2a. Negative 2 times 1, negative 2. Now what's on the bottom? On the bottom we have 7a minus 4. So this is what we had. This is what we end up with. So this one brought in some different skills. So each question has a little difference to it. Okay? So now let's go to the last rational expression, and then we transition over into some simple rational equations. And the next time we meet, we do more complex rational equations. Okay, here we go. So this is number 9. It says 12 over C plus 5 minus 4 over C minus 5. Ooh, all divided by 8C over C squared minus 25. That's what is given. Let's see what we get. Okay, here we go. We're going to get a common denominator. So the common denominator is a product of these two denominators. So we're going to end up with C plus 5 times C minus 5. That's our common denominator. Just multiply the two denominators. So this, we have to multiply this by C minus 5. So therefore we have to multiply the top by C minus 5. So now we have 12 times C minus 5 minus 4. What did we do to the bottom here? We multiplied by C plus 5. So we have to multiply the top by C plus 5. Okay, let's go to the bottom. When I look at this C squared minus 25, I say C squared minus 5 squared. So it's a difference of squares. And we know the factorization of that is very common. So it's going to be 8C over C plus 5 times C minus 5. That's the factorization of this. You can check it. You will see that when you multiply these two, you will get that when it's simplified. So here we go, right at the place where we want it. One fraction divided by another fraction, we flip and multiply. So here we go. In the process, I need to simplify the numerator also. So we end up with C plus 5, C minus 5, and that gives me 12C minus 60, and then that gives me minus 4C minus 20. And now I'm going to multiply by, I'm going to flip this. So it's going to be C plus 5 times C minus 5, all over 8C. If you look carefully, you see that this cancels that, and this cancels that. So now what are we left with? Well, 12C take away 4C is 8C. Negative 60 minus 20, negative 80. All over 8C. So if you look at this, we can divide the top and the bottom by 8. And we end up with C minus 10 all over 8. And that will be our final, sorry, all over C. 8C divided by 8 gives me just C. So divide this by 8, we get C. Divide this by 8, we get negative 10. Divide this by 8, we get C. That's our final answer. So we move from this to this. So now we are ready to transition into solving rational equations. Okay. Let's start off very simple, and then we'll build it up. Okay, let's start with something simple, and then we'll take it up a notch. Okay. My recommendation, just as a general approach to solving rational equations, is you're given a rational equation, try your best to eliminate all denominators and then work from there. Once you convert everything, once you eliminate all denominators, then you're on easy street. So the challenge really is, how do you get rid of all the denominators? That's the challenge. So here we go. So now we're starting afresh. This is solving equations. So if we had 1 over x equal to x over 9. This is a classic example of what many students like to refer to as cross multiply. Cross multiply. So you take this and multiply times that, and you take this and multiply times that. To make it simple, in order for me to get rid of the denominator x and the denominator 9, I need to multiply the whole thing by 9x, which is the common denominator. Think about it. So if I multiply the left-hand side by 9x, I get 9 equal to, when I multiply this by 9x, just multiply by 9x, just multiply by 9x. This x cancels that x, I get 9. This 9 cancels that 9, I get x squared. So now I have x squared equal to 9. So now I know that because of this square, I have 2 answers. The degree of my equation tells me how many answers I have. So if I had a cube, I would have 3 answers. If I had the power of 4, I would have 4 answers. So if x squared is 9, then we know that x is equal to plus or minus the square root of 9. X is equal to plus or minus 3. There are our 2 answers, positive 3 or negative 3. Okay, let's try another one. So in summary, how did we tackle the question? We got rid of both denominators. How did we get rid of the denominators? We multiply both sides by the common denominator. Here's another one. Number 2. If we had 4 over x equal to x over 4. Again, 4x is my common denominator. So therefore, if I multiply both sides by 4x, I end up with 16 equal to x squared. So therefore, x equal to plus or minus the square root of 16 plus or minus 4. And then you're going to say to me, oh, these are very easy. And I will say to you, not so fast. Let's try another one. 3x over 4 equal to 5x plus 1 over 3. Okay, so what's the common denominator? With 4 and 3, the common denominator is 12. Okay, so if I multiply this side by 12, and I multiply the other side by 12, what do we end up with? 4 into 12 goes 3 times. 3 times 3x is 9x. 3 into 12 goes 4 times. 4 times that gives me 20x plus 4. And then I need to get everything on one side, all the x's on one side, and all the constants on the other side. So here we go, subtract 20x. I get negative 11x equal to 4. Divide both sides by negative 11. I end up with x equal to negative 4 over 11. So that's number 3. Again, not complicated. We're going easy to start, and then we will build up. Let's see if this works better. Let's go to number 4. Okay, number 4. We have 4 over x plus 1 equal to 5 over 3x plus 1. Again, a rational equation. You have a variable, you have a fraction with variable. So again, if I multiply both sides by x plus 1, I multiply this, so cross multiply, we will get rid of the fractions. So if I multiply this side by x plus 1, I'm left with 4, but then I end up with 5 times x plus 1 over 3x plus 1. Then when I multiply both sides by 3x plus 1, it cancels this denominator, and then it's going to be 4 times 3x plus 1. Or you could say cross multiply. So it's this times this, this times that. So we end up with 4 times 3x plus 1 is equal to 5 times x plus 1. And now it's an easy question. We just expand 12x plus 4 equal to 5x plus 5. Subtract 5x, 7x equal to subtract 4, 1. So therefore x equal to 1/7. Math remains the same. The math remains the same. I could have said to you, I'm multiplying both sides by x plus 1 times 3x plus 1. When I multiply this side by x plus 1 times 3x plus 1, the x plus 1 cancels the x plus 1. So we're just left with the 3x plus 1. There it is. When I multiply this side by x plus 1 times 3x plus 1, 3x plus 1 cancels 3x plus 1. I'm just left with x plus 1, 5 times x plus 1. Then I distribute, and then I combine like terms, and there it is. Let's do another one. Okay. I'm going to do one more question like this, and then we're going to go into something more complex. Okay? One more question like this. So here we go. 3. This is number 5. 3 over 2x minus 3 equal to 1 over 5 minus 2x. When you just have a fraction on the left and a fraction on the right, you can use the concept of cross multiplication. So this becomes 3 times 5 minus 2x equals to 1 times 2x minus 3. And then what do we end up with? 15 minus 6x equals to 2x minus 3. Combine like terms. So we could bring this over here. We end up with negative 8x equals to negative 18. And then we divide both sides by negative 8. We end up with x equals to 18 over 8. Or x is equal to 9 over 4. Don't give a decimal, just leave it as a fraction. Okay? Making progress, making progress. Let's go to one that's a little bit more involved. Let's go to something a little bit more involved. Number 6. Okay, number 6 looks like this. So my markers are starting to fail me. Let's see. Number 6, we're going to go for x plus 10 over x minus 2 equal to x squared plus 3x over x minus 2. X plus 10 over x minus 2 equal to x squared plus 3x over x minus 2. Good. Okay, so again, our goal is to get rid of all the fractions. Remember we talked about that? Get rid of all the denominators. If we get rid of the denominators, then it becomes easy. So this is x over 1. So if we multiply both sides by x minus 2, you see the denominator? Common denominator is x minus 2. What happens? Well, we end up with x minus 2 times x over 1 plus 10 over x minus 2 equal to x minus 2 times x squared plus 3x over x minus 2. When I multiply this times this, I end up with x squared minus 2x. When I multiply x minus 2 times this, they cancel, and I'm left with just plus 10. Very important, very important. You have to multiply this times this, and this times that. So when I multiply this times this, I get x squared minus 2x. When I multiply this times this, the multiplication and the division, they cancel. And I'm just left with the numerator 10. Over here, when I do x minus 2 times this cancels that. I'm left with x squared plus 3x. And as I look at this equation, I say, oh, x squared on the left, x squared on the right. So I subtract x squared from both sides, x squared is gone. We have negative 2x plus 10 equal to 3x. We could add 2x to both sides. So we end up with 10 equal to 5x. So therefore, x is equal to 2. Okay? Now, truth of the matter is, if we were to go back and check and plug in this 2, we would discover that it actually creates a problem. But this is the mathematical solution for this, and therefore, that's what we get. Why am I saying this? Okay? This 2, if we were to put 2 here, will give us 2 minus 2 is 0. 10 divided by 0 is undefined. Okay? And whenever there is a number that is a solution to a mathematical problem, but it does not make any practical sense, we refer to that solution as an extraneous. An extraneous solution. What does that mean? It means that mathematically it solves the problem, but practically it's of no use. Make sure you get that. Mathematically it solves the problem, but technically it's of no use. X equal to 2 is what would solve this algebraically, but when we take the 2 and we try to plug it in, it will not work, because 2 minus 2 is 0, and you cannot have 0, you cannot divide by 0. Where does that happen in real life? I'll show you an example. Okay, so we're going to do an example of extraneous solutions in real life. Okay. Okay, let's keep it simple. Let's keep it very simple. Suppose there's a room that is a square, and I say that the area is equal to 225 meters squared. And I ask you, what is the length of each side of the room? Well, you know that area is equal to length times width. So therefore, this times this gives me x squared equal to 225. So you have an equation that is a quadratic equation. It has a degree of 2. And mathematically, we say that the degree of your equation tells you how many solutions. So you ask yourself this question: what value of x, when you square it, you get 225? The answer is x has to be equal to plus or minus the square root of 225. So x has to be plus or minus 15. But we know that the room cannot have a length of negative 15. We know that x must be 15 meters. Okay? X is equal to 15 meters. So the negative 15 is called an extraneous solution. Because you cannot have a negative distance, you cannot have a negative length. It's just like you cannot have a negative weight or a negative height. Meaningless. You can have a negative balance for those people who love to use credit cards. Okay, so that's the concept of an extraneous. So extraneous solution means that that's the algebraic solution, but it does not have a practical relevance. Got it? Extraneous. Remember that word will come back. Extraneous. Extraneous solution. Okay, how are we doing? I'll do one more question and then that's it for today. Okay, I'm not sure what number we're on. Let's call it number 7. So let's go. Okay. So 1 over 2x plus 2 plus 5 over x squared minus 1 is equal to 1 over x minus 1. And you're asked to solve that. So let's go. My recommendation is factorize where possible, and then you get a common denominator. So for this one, I will do this as 1 over 2 times x plus 1 plus 5 over, if you look at this, you will see that it's actually x plus 1 times x minus 1. And then over here, it's 1 over x minus 1. So what's my common denominator? My common denominator is, it must have x minus 1, it must have x plus 1, and it must have 2. So my common denominator is 2 x plus 1, x minus 1. That will work perfectly. So what I'm going to do now, I'm going to multiply the left-hand side, or an easier way to think of it is that, okay, multiply everything by 2. So that will get rid of the 2 from the denominator. Then multiply everything by x plus 1. That will get rid of the x plus 1 from the denominator. And then finally multiply everything by x minus 1. And that will get rid of the denominators that have x minus 1. But why not do it in one step? Instead of doing it 3 different times, multiplying by 2, multiplying by x plus 1, multiplying by x minus 1, you could do one step, multiplying by the 3 things at the same time, save you space and time. So I'm going to multiply by the 3 factors, 2, x plus 1, x minus 1. So when I multiply this by 2 times x plus 1 times x minus 1, the 2 cancels the 2, the x plus 1 cancels the x plus 1, and we're left with x minus 1. Plus, when I multiply this by 2 times x plus 1 times x minus 1, these cancel, and we're left with just a 2. 2 times 5 is 10. We go over to the right side. When I multiply all of this, the x minus 1 cancels the x minus 1, and I end up with 2 times x plus 1. So look at what we have. We transform this complex looking rational equation into something that is a very simple linear equation. So what is this? So this becomes x plus 9 equals 2x plus 2. Okay, subtract x from both sides, subtract 2 from both sides. We end up with 7 is equal to x. It's always good to write the variable on the left side. So the question is, suppose I plug in 7 for x. Would the left side be equal to the right side? It better be, otherwise there was a mistake. So let's try. If I plug in 7 for x, this becomes 1 over 16. Okay? So it's 1 over, where can I write this? Can I write this here? So that becomes 1 over 16 plus 5 over 7 squared is 49. Take away 1 is 48. Common denominator is 16. Sorry, it's 48. So this has to be 3 times 16 gives me 48. So the top is 3. So we end up with 3 plus 5 over 48, which is equal to 8 over 48, which is equal to 1 over 6. When x is 7, 7 minus 1 is 6. 1 over 6. It works perfectly. So we have dealt exhaustively with rational expressions. We have simplified at least 16, 17, 18 rational expressions between the last session and this session. So we have done a wide variety of rational expressions, simplified. Today, we have done 7 questions on rational equations. There are still more complex examples. So in our next session, we'll finish up rational equation. On behalf of the Brosis Foundation, we thank you for spending this time with us. We know that you have benefited from this, otherwise you would not be here. We plan to continue to give you quality product so that you can improve your skills, not only in math, but also in English. So again, on behalf of the Brosis Foundation, we thank you and we wish you a wonderful rest of the day.